Hello, here's a starter question for you. We're dealing with the probability distribution of a variable, a random variable, which can take the values 2, 3 or 4. There is something wrong with this probability function, so explain why you know that can't be the probability function, and given that this is the probability function, find the value of k. So pause now and have a go at those two. Okay, so hopefully A was pretty much okay using, sorry, I can't see the question anymore, but using the formula here, those were the probabilities you got, but they didn't add up to 1, so that can't have been. So with B, using the formula here, this is what I got. I know those had to add up to 1, and this was a horrible fraction addition sum. 144 was the denominator I went for. I suppose if you, on your calculator, added 1/4 plus 1/9 plus 1 over 16, that would have helped you out. But anyway, that's what I got on the top, having got a common denominator of 144. Added those together and got 61k. So 61k over 144 is 1. I know those probabilities have to add up to 1. So that was my answer. Don't worry about this comes later. So that was my answer to that one. And if you got that, well, hats off to you, because I think this was a particularly tricky example. I'm sort of hoping everyone was okay with this. So we are dealing today with a particular sort of probability distribution. Now, probability distributions describe probabilities of random variables. There is no predictability in the value that comes up of a random variable. However, the patterns you see in probability distributions are sometimes predictable. And the binomial probability distribution, which is a distribution with particular properties that we're going to go through in detail, is one such distribution. Now, this word is a word that we have used very recently in pure maths, so it's quite interesting to do this now. I want to start by talking about table tennis. Okay, some of you know I quite enjoy a game of table tennis, and even though I say it myself, I'm quite good. South Suffolk under-19 singles and doubles champion back in the day. Anyway, let's imagine that I decide to take one of you on at table tennis, and I know a number of you are quite good yourselves, so I'm going to pick Jacob Kingsmith. I believe we may have even played before. Let's say that Jacob and I play 5 games of table tennis, all right? And I'm talking about this from my point of view. So let's say that Jacob's a really good table tennis player, but let's say that the probability I win is 0.7. Now, I'm not going to tell you how I've worked that out. It might be in the past we've played 10 games and I won 7 of them, but let's say that the probability I win is 0.7. And we play 5 games, so I want to do the probability distribution, which is the number of games of those 5 that I win. Okay, so I might not win any of them. I might win 1 of them. I might win 2 of them, 3 of them, 4 of them, or of course, all 5 of them. And I want to work out the probability of each of those values. So we've got here a probability distribution. It's created by this scenario here. 5 games, and the probability I win is 0.7. Now, I'm making a couple of really quite important assumptions in that. The fact of the matter is that as you play someone at a game a lot, you can modify the way you play to respond to them. So I've got a bit of a dodgy backhand, so it might be that after a few games, Jacob starts really working on my backhand, so this probability might change. We've got to assume that it doesn't. Okay, so for us to be able to work out these probabilities, we've got to assume that this probability doesn't change. There's a couple of other assumptions that we'll come to. Okay, let's work out the probability of each of these. Let's start with the probability that I don't win a single game. I lose every game. Impossible, I hear you cry. Almost certainly true, but let's work it out anyway. So the probability that I lose the first game is 0.3. And in the second game, 0.3. Remember, we're saying that we're assuming the probability doesn't change. So are you happy? The probability that I lose every game is 0.3 to the power 5. because it's 0.3 times 0.3 times 0.3 times 0.3. Okay, what about the probability that I win one game? I'm hoping you can see that that would involve Jacob winning 4 games, 0.3 times 0.3 times 0.3 times 0.3, and me winning 1 game. But that's not the right answer to what's the probability I win 1 game. This is only one way that could happen. This is Jacob winning the first 4 and me winning the last. But Jacob could win the first 3, I win the 4th, and then he wins the last. Or he could win the first 2, I win 1, and then he wins the last 2. Or he might win the first 1, I win 1, and he wins the next 3. Or I win the first and he wins the next 4. Can you see how each of these is going to be the same answer? Because they all involve 0.3 to the power of 4 times 0.7, albeit in a different order. So the probability of this is this multiplied by the number of ways it can happen. The number of ways you can win 1 of 5 games. Now that's easy to work out in this case, it's 5 different ways, but it's actually 5C1. 5C1 is the number of ways you can select 1 from 5 things. Now, is this beginning to look familiar? Let's work out the probability that I win 2 games. Okay, so the probability I win 2 games would involve Jacob winning 3 and me winning 2. But again, this is the probability that I win the last 2. I'm not going to list them all out, but I could win the first 2, or I could win the first and the third, or the first and the fourth, or the first and the fifth, second and the, there's a lot of different ways that can happen. It's 5C2. 5C2 is the number of ways you can choose 2 things from 5. So if you've got 5 people and you want to choose 2 people for student council, that's the number of ways you can choose them. In this case, it's the number of ways you can choose 2 of the 5 games for me to win. I'm sort of hoping that familiarity is sweeping over you. So go on, see if you can, without doing any sort of thinking, see if you can continue the pattern for the remaining probabilities. Pause and have a go. So I'm hoping that you were able to get that. This is very much like the binomial expansion from Pure, isn't it? We're not adding these terms together. These are the individual probabilities, but the pattern is just the same, isn't it? And why is there no NCR here and here? Well, we know this is 5C0 and this is 5C5, and both of those are 1. We also know that there's a symmetry to this pattern. We get that from Pascal's triangle. So I could also have got those from Pascal's triangle. So, I've got 1, 5, 10, 10, 5, 1 would be the answer. So this is why it's a good time to do this straight after doing binomial. The only thing is, we're not dealing with a plus b to the power of 5, are we? Which is the sort of pure equivalent to this. What are we dealing with here? Well, what we're saying is that, what we're saying is that the value of x, remember x is the number of games I win, the value of x can be modelled as a binomial distribution where we're doing something 5 times, and every time I do it, the probability of success is 0.7. So this is a funny little sort of, it's like, when we do approximately equal to, you do a squiggly equal sign, well that's like one of the squiggles. We're saying x can be modelled as a binomial distribution, a binomial probability distribution, where we're doing something 5 times, and every time we do it, the probability of success is 0.7. So the binomial only works in certain situations. It only works where you're doing something repeatedly a fixed number of times, and every time you do it, there's a sort of success-fail scenario, and the probability of success stays the same. We call this number n, and we call this value p. 0.3 is 1 minus p. Sometimes the letter q is used for that, and I suppose that's a bit like the a and b from the pure version. So we can work out individual probabilities to complete a binomial probability distribution. And if I did work out all of these answers, I have no intention of, but if I did, they would all add up to 1, just like any other probability distribution. So let's have a look at a slightly different question. So here we are told about another random variable. This time it isn't the number of games I win out of 5. In fact, we're not given the context at all. We're just told that this random variable can be modelled as a binomial probability distribution where whatever we're doing it 12 times, and every time we do it, the probability of success is 1/6. So this might be rolling a dice 12 times, and x is the number of 6s you get, because the probability of getting a 6 is 1/6. And I said that you need success-fail criteria, so in this case, success would be getting a 6, and fail would be not getting a 6. That would be a probability of 5/6, wouldn't it? So the probability that x is 2, well, just like the binomial distribution in pure maths, my answer to this, just like each term in the expansion, will have 3 parts to it. So I've got, if I'm winning 2 times, I'm going to fail 10 times, and I'm going to win 2 times. And it doesn't matter which way round I do those two, obviously. But don't forget you also need 12C2, because that probability there is just the probability that you fail for the first 10 goes and you succeed for the last 2 goes. There's obviously lots of different ways you could get 2 successes out of 12, and that's why we multiply it by 12C2. So I can type that in on my calculator and get my answer. So have a go at that, and then see if you can answer this one, and then this one. Pause and have a go. Actually, let me just remind you how to get NCR on your calculator. So you go to Option, second page, Probability. There it is. Go on, have a go. Okay, so I hope you were putting your fractions in brackets. Remember, that's the power button, the little hat. If you obviously you've got a squared button, but any other power you need to use the hat. So we get for this, a tiddly tiny number, which I jumped back to get me that. Now, interestingly, you know we default to 3 significant figures everywhere else. We tend with binomial to use 4 decimal places. Now, there's a reason for that. We'll talk about next lesson. So I've gone with 4 decimal places for this one. This one I didn't really know what to write because it was so tiny, but I wrote, so that's 4 significant figures, isn't it? And did you get this right? Less than or equal to 1, so that's 1 or 0. Don't forget 0. So, you know, you might not get 1 at all. So you've got 12C1 times 11 fails times 1 success added to 12 fails. And add those two together, and I got that to 4 decimal places, and hopefully you're okay with that one. So we've looked at 2 examples, one in context, Jacob and I playing table tennis, and one out of context. We were told about some random variable, and it was something we were doing 12 times, and the probability of success was 1/6. Here's one in context again, but you may notice there's no mention of the binomial in here at all. So this question, you would be expected to recognise it as a binomial problem, and in fact that's what part A is all about. So part A, we're saying we've got 20 members, we take a sample of 20 members from this group. We've got the probability across the whole group of getting a left-handed person of 0.15. So X is the number of members in the sample who are left-handed. So what they're trying to get you in part A is to say, okay, yeah, the number of left-handed people can be modelled as a binomial distribution because we are picking someone 20 times, and every time we pick someone, the probability of success is 0.15. Now, again, you could argue that that is a dangerous assumption because obviously as you take people out, then the probability might change. But this is the thing, this is a model, so it's not perfect, but it is an attempt to try and work out probabilities in a real life situation. And justify your choice, you'd be expected to say we are modelling it as something we're doing 20 times, and every time we do it, the probability stays the same. We'll talk a little bit more about the assumptions next lesson. But my question is, given that that's the answer to part A, can you answer part B for me? Have a go. Okay, even on YouTube I move things up regularly, so yeah, so that one, 4 decimal places I've gone for. I note the book uses 3 sig figs. You'll see mark schemes use 4 decimal places. Anyway, it doesn't matter, it's not crucial, you would get 4 marks, whichever you did. 0.0160 using that sum, and then less than 2, so that's 1 or 0 added together. So I worked out that and added them together to give me that. So a situation can be modelled. So the fact we're using the word modelled means that it's not perfect. Trying to take a real world thing and force it into a model, it's never perfect, but we can model it if we've got these things true. So if it's something we're doing a fixed number of times, so it doesn't work if you are for driving tests, for example, because you don't take your driving test a fixed number of times, you keep going until you pass. So it needs to be a fixed number of times. You need to be doing whatever it is a fixed number of times. You need success-fail criteria. So you could say, well, I can't use it in football matches because there are 3 outcomes, win, lose, draw. Well, you can, you just have to say win or not win. Fixed probability of success, so like my example with Jacob and table tennis, we're assuming that, the probabilities of me winning don't change. It's not particularly realistic, but we have to assume that. And the trials are independent of each other. So just because of what happened, if you pick someone who's left-handed, it doesn't mean you're more or less likely to pick the next person left-handed. You don't tend to get left-handed people huddling together for security in this world. So, that was an okay assumption. But if you were talking about people with a particular, testing for a particular genetic condition, and you were testing people in families, then, the fact you found someone with it, you may find that that affects the probability that the next person is going to find it. So these are the 4 criteria we need in order to be able to use the binomial distribution. So I've got a couple of questions for you to try for independent study. Question 2, which is another out of context question. And then question 4, which gives you some scenarios and just says which of these are appropriate for the binomial. Which of these have all of those conditions. And that's it for today, except to say, I don't know about you, but I'm already a little bit tired at typing in all those long sums. If only there was a better way of doing it. Well, do you know what? There is a better way of doing it. The calculator does it for us. And I'd like to show you that next lesson. And because I really think it's something that we need to get clear, and I don't want you to be confused, I'm going to do that next lesson, therefore, as a live lesson. So that will be Monday for 12E and Tuesday for 12B. And I'll set those up on Teams. That'll be period 5 on Monday for 12E. And I'm sorry, I forget my timetable for 12B. You're welcome to come to either of those. And if you want to come to the one you're not invited to, I'm sure there's a way that you send me an email or someone else can invite you. I don't know, I'm sure you probably know better than me. But that's what we're going to do at the beginning of next week. I think that will just be really helpful so I can actually make sure you can all use it. So for that lesson, Monday or Tuesday, make sure you've got your calculator with you. Make sure it's batteried up. If any of you have got problems with your calculator, please email me before Monday or Tuesday so we can sort those problems out. Okay? don't forget to have a go at those two questions, and I will see you next week.